Nếu mà máy ông không còn bộ nhớ, ông có thể stream thẳng lên YouTube luôn, nó sẽ lưu cái stream lại cho nó, ông không cần phải có gì chạy vô máy.
Ok, được, không sao,
Nếu
được,
mà
không
máy
sao.
không còn bộ nhớ.
Rồi, mấy ông thấy màn hình bên nghe rõ hết đúng không?
Rõ rõ rõ.
Ok, ok, vô nha, vô nha. Okay, let's start a new sheet and let's go. We'll talk about physics simulation. Cứ phải cho người vô này. Physics simulation, and what is it? And why am I talking about it? Because I have been talk a little bit about myself. I've been researching about this for the last 9 months, so I think that I know some basics that can be beneficial to you. So I'll share it to you, and I'm talking in English because, you know, we are in the English class, so maybe this gonna be more close to the official curriculum. So what is physics simulation? It's basically you simulate the physics on a computer, because when you are observing a physics phenomenon, you cannot observe all of them in real life, and also you have to idealize the condition, because in real life a physics phenomenon can be affected by thousands of things that you cannot control. So you have to find a way to idealize your physics engine, so that you can plot the graph, so that you can predict the weather, so that you can see the physics in terms of equations, like you can manage it, you can manipulate it however you want. And that's why we put physics on our computer. And there are some kind of physics simulations I want to tell you. First one is like you use physics simulation to do robotic, like I can see robotic, MATLAB, ARM, like that. And you could see some here. This is the simulation. Right. Or you can use CFD. CFD is a fluid simulation, so that you can stress test, like you're building a pipe or a dam. You would like to stress test the fluid, so you assure that the pipe won't break while you are building your house, like that. Here, you see. Or sometimes you would like to simulate physics, because you are making a game engine. There will be like physics engine C++, and you will find that a lot of video talk about this. You do it for games, because in games, you know, you have to make collisions, right? You want to make a physics engine. Here is the physics engine. Okay, so talking about the most important concept of physics simulation, it's gonna be the first section. Okay, we're gonna talk about discretization. Why we have to discretization? Cái này chính là cái sự phân khúc, ý là discretization là cái sự phân chia nhỏ ra. Ok, hình như là viết sai đúng không? Nó phải là discretization. Okay, for example, in our world, if I have a axis of x and y here, and t, x and t, like I throw an object in the air, okay, it's gonna go from this, gonna go all the way and hit the ground. This is in real life. I recorded this information in real life, so I know that every time section that I break down, there's gonna be a value of x. Like in 1.57 seconds, x gonna be 9 meters. Okay, here I can choose any time I like 9.206, like that, and I will have the same, I assume, okay? But if I want to simulate this on the computer, I cannot have a infinite set of time, because computer we work with data, and the infinite number of time will result in the infinite number of data, and it can be like 1000 gigabytes, 1 billion gigabytes. No supercomputer can handle that much. So first we will have to do time discretization. Có thằng xin code phòng từ từ. We will have to do time discretization. Hold up. NGW FGKD PZG. Okay? Which means that we will divide our continuous field of time. Here, we divide our continuous field of time into what? Into sections, not sections, into parts, into discrete parts. Okay, that's the first thing. We have a limited memory, so we will have to dissect our time into finite things. So this is real life, okay? This is real life. This is real life data. And it's gonna be infinite time steps. And this will be approximately our computer version. In this version, the time will be sectioned into parts, like I can 1 second, 2 seconds, 3 seconds, 4 seconds, 5, 6, 7, 8, 9. And I only store the value of x in these discrete time steps, and I will have the total of 5 data, okay? 5, let's see, 5, 6, 7, 8, blah, blah, blah. This is what the computer expects. Okay, so I'll have the total of, let's say, 10 seconds, I will have 10 vectors, 10 vectors, finite vectors, okay? Fine, that's the first one. And then we will have to do one more thing. We will have to, if we can discretize the space at the time, we will have to do it for the space as well. We have to do space discretization. Because if a computer cannot store an infinite number of time steps, of course it cannot have a interface to show an infinite point in space, right? The limit of a computer is pixels, right? In this computer, I can see a lot of colors, I can see a lot of images, but actually they are discretized into pixels. Okay, basic concept, we can think of pixels. And just like that, when I'm simulating a projectile, this is a projectile, okay? This is a projectile. I'll have to discrete the space. Like I cannot have any value of x right here. I can only have like this 1 meters, 2 meters, 3 meters, 4 meters, and 5 meters. This is not applied for everything. Like I guarantee you that you will always need to discretize the time. But about the space, it can be optional. The space is optional. It depends on what you are trying to simulate. Because if you are simulating a projectile, okay, then you don't, okay. There are gonna be two things. If a point mass, like a vector tree, vector 3 position. If you only have to simulate point mass and they are described by the x, y, and y coordinate, then you can store it in terms of vector 3 position. Okay, then you can have any value. But if a continuous field, like I'll take example, you are simulating fluid. Fluid is a continuous field, right? Fluid, or you are simulating a soft body. Soft body is a body that can be distorted when you apply some force onto it. Then you will have to discretize. Then it can only store finite values. Because if you have a point mass, you can move your vector 3 and you just have to update the value of it, right? So you don't have to care about how many space my computer is available. You just update like 1.79, 2.00, you can update any value. But if it is a continuous field, like this, your computer cannot handle infinite points. Right? Cannot handle infinite points because this is a fluid field, right? It means that every point, every infinitesimal point in this field, it has data. It has data. So your computer cannot let me see. Computer cannot store infinite data. Okay? So when you're simulating a continuous field, you have to discretize it, and that is the space discretization. Two things, time and space. Okay. And one more. When do you have to do space discretization? It is when space discretization occurs when plotting. It means that when you are trying to plot, you are trying to draw a graph, right? You have to choose the gap between each value. Like this graph, my computer is not continuous, it is divided into pixels. So when I'm plotting the graph, these numbers is confined by some limit. Like this one, like this note, it is discretized into grids in space, right? So when I draw a graph or when I draw a surface, I can draw a surface like this. You will often see the grid-like structure here. Or I can take MATLAB for example. I will open my project here. I will hit run. Where's the run? Where's the run button? Run in time. Oh, not it. Oh, I forgot how to run MATLAB. Okay, you can see later that you have to discretize the space in order to plot the data. Okay. Hold up. How can I run this? Where is the run button? Plot, run, go. What the hell? Ê, hey, anh đã giúp tôi với. Làm sao để chạy này vậy? Đây, okay. Here, you have the graph, right? Okay, you have the graph. Then you have to discretize this into, you can see a little squares here and squares everywhere. Okay, you can only store a finite set of numbers, so you need a finite number of finite number of the axis you are trying to plot, so that you can input each data into a value in that axis, and it can still be finite. Okay. And let's see the second one. Second one is the numerical solution. How do a computer simulate a projectile? Take the projectile for example, okay? Take projectile for example. Yeah. When you can describe the trajectory of the projectile into a function, right? You have the Newton's second law, right? You have the second law of Newton. A projectile is affected by mg, and also maybe some will describe it with the additional fc. Fc is fd. It's like the drag force of the air that will slow down the projectile as it travels through the air particles. So basically, the second law of Newton says that Fd plus mg equals ma, right? Ma. And then I assume that my Fd, my F drag, is equal to a constant, and the v vector, okay, plus mg equal, and the a here is the derivative of v, right? Is dv over dt, and I can expand it onto two axes, the x and the y axis. On the ox, it can be minus kvx equal mdvx over dt, and oy can be minus kvy minus mg equals mdvy over dt. Okay, so basically we can solve let's see this equation 1 analytically. Then we will have some function of vx with respect to t and vy with respect to t, and then we can get the exact solution of x, t, and yt. Okay, this is the exact solution. This one is exact solution. Why? Because you can input any t into those functions and you will have a value, and that value will be the exact value that you expect from the second law of Newton. You solve this equation. Okay? But if you notice, you can only solve this equation if it is easy. Like I only have two things here. Some problem will involve the spin, the Magnus effect too. The spin of this, I assume this is the Magnus effect, okay. Effect, then the second law of Newton can be minus kv plus the I over the d omega over dt, and it can be everything. Okay, the r maybe, and it can be everything. It can be very complicated. Can get complicated very fast. If you want to add more effect so that it looks more like real life. In real life, we don't only have the drag, only have the gravity. We have thousands of things that you would like to consider. Then you just cannot get the analytical solution, right? Maybe some master of math can solve this, but it's gonna take ages. We don't like that. We have the computer. So how? This is where we need numerical solution. or I can say numerical solution is approximation. Okay, it is the approximation that we it is the approximated value at the output. Okay, I'll take this one for example. We have minus kV plus mg equals m dv over dt, right? I'll call it at the A. Then, what are the steps to solve this in your computer? First one, you input initial conditions. Okay. And in this example, you will input V0. And V0 could be a vector of Vx, Vy, and Vz. Okay. The second step, instead of solving for this one, you would like to solve for the function. You would like to see the x and the y coordinates of this projectile in any time, in any given time. So you can input this V0 into here, and then you will calculate whatever you can. Basically it. If you have this function, you can input V0 into here, and then you will have minus kV0, right? Plus mg equals m and a0. And you can get a0, okay? a0 equals something. And then you will use this a0 to update your v0. You all know that the a is the derivative of v over t, right? Right. So if you want to update v, first you have to do what? You have to do time discretization. It means that instead of writing this infinitesimal delta, you will change this to a equal a delta v over delta t. And delta t is finite. You can use like 0.001 seconds, for example. The smaller your time step is called time step. Okay, time step. The smaller your time step is, the more accurate and less and more stable your simulation becomes. Okay, and here you can see that a0 will be equals to v1, right? v1 minus v0 over delta t. And then you can directly solve for v1. You can use v1 equal v0 plus a0 delta t. And then you have v1. What you do with v1? Okay, the initial condition, you have to have x0 too. It's gonna be xyz. You solve for zt too. Assume we are working in the third dimension. Okay. Then you will have v equals delta x over delta t. Then you will have v1. Actually, v0 equal x1 minus x0 over delta t, and you will have x1 equal x0 plus v0 delta t. And then what you do? You plug this v1 into your equation, right? And then you will have minus k v1 plus mg equals m a1. Then you will have a1. Then you will have v2, right? You have v2. And you will use this v1 to get x2. Okay? It means that instead of you try to solve your equation, you will break it down into discrete steps, and then you will build it from the bottom to the top. You could build the acceleration, then you take the acceleration, you build the velocity, then you use the velocity, you build the new position. Okay, so basically it will be the loop. The loop is like this. First, you will discretize time into time step dt. And you will see that the smaller the better. The better. But it's gonna be more costly, okay? More costly. Because more smaller dt means that you have to store more information in order to get your simulation working, so your computer will have to work more, to loop more. And then you will input initial value. Then you will update each value one by one. Okay? Each value one by one. For example, you can update the A, then you get the V, then you get the X, then from like A01, V1, X1, then you use the X1 till you get A2, then you get V2, you get X2. So this loop will be for something in the range of your simulation step, your expected time. Okay, and it's gonna be forever. Okay, update each value one by one, and maybe you can solve for constraints, and we'll talk about constraints in the later section. Okay, that's the basic concept. You will always have to discretize a function in order to solve it on your computer, and after you discretize it, you input your initial value, and you will let the system evolve. Evolve itself. You don't have to do any math anymore. You just have to code a loop, and you just press enter, and the computer will loop over this loop forever. It will get A1, V1, X1, A2, V2, X2, A3, V3, X3, and you can store. Then you can store this in your arrays, okay? In arrays. And you can retrieve the data you want. Okay, that's the basic concept. Like if you look at this simulation, I am plotting the trajectory of a charge in this energy field, and you can see that my code, I loop over it many times here for I, and I will loop it from to the number of steps that I want, and I will input the x, the y value, and I will calculate, then I will use this value to calculate the force, and I will have the acceleration, and I will have the velocity, and I will use the velocity to update my x and y with and I will have x equal x I minus 1, I plus it to vx, and I forgot the name for it. Nhân, phép nhân đấy. Nhân nó với một cái dt nhá. Rất bé, một cái dt rất bé, nhưng mà cái dt của ta là xác định. Dt is fixed. Okay. And we will talk about the third section. It's about the solvers. Why do we need solvers? Because not because solvers is basically the algorithm. It is the algorithm. Algorithm to solve for numerical solution. Right? We know that, okay, now we won't treat it like a normal equation. We will treat it as something that a computer can handle. So we need to find an algorithm to solve the system that we want. This is just a basic example for a point mass. There are going to be a lot of algorithm for each type, each category that you're simulating. This is one of them, and I will introduce you some basic solvers and their attributes. Okay, the algorithm to solve for. A solver can be explicit. It can be implicit. And the second set is it can be exact, and or it can be iterated solver. Okay, what are these? What are these? Explicit is what I've done for you to see. Explicit means that we update one by one. So basically, it is the easiest. Okay. Like you have the x, y, z, the x, the v, and the a. You update them one by one. You have the x, you update the a, you update the v, you update the x, and the implicit means that you update them as a whole. Okay. Explicit, you will have a loop here. You have a loop of x, and you will solve for a, then you will solve for v, and from v you solve for x. What's the implicit? A is a function of x, right? I assume that a is a function of x, and maybe x is a function of x is a function of v, like this. Then there will be a number of functions that you have to satisfy at once. This thing, you have to satisfy a number of equation at once, and that's where you have to build a special solver for that. Explicit is very easy. You update them one by one by one, but if you look closely, each of them is related to each other, so it will be best to solve them simultaneously, and that's the implicit one. It's harder, it's much harder. And I'll talk about the matrix and constraints. Matrix is basically a set of equations, right? Like I have a matrix, I can here A must sleep, like that. B must study, or C must go jogging, right? Then I will have to satisfy all of these things in order to have a happy family. In order to have a happy family, A must sleep, and simultaneously B must be studying and C must go jogging. So matrix is basically a set of equations. It's not like that, but you can think of it is it will store a set of equations. And constraints are also constraints. Oh, this is not matrix, this is constraints. Okay, constraints. Constraint. Or in a rigid body, you will have what constraint? You will have like the jot A has to be connected to C, okay? Like C must be connected to the ground. Like that. Like you will have a lot of sticks that they have to connect in each other in some way, and that's where you will have to solve for constraints. And there are two ways to solve for constraints. There will be a exact and iterative. An example of a exact solver is the Gauss elimination. You can search for this on Google, okay? And the second one will be Jacobi solver. So basically, the intuition behind the exact solver is just like our implicit, meaning that you will find some way to satisfy everything perfectly. It's like you solve the equations analytically, okay? But for the iterative, you solve each constraint one time. Okay, I'll talk about the iterative. You solve constraint in an order. You solve for number 1, then you solve for number 2, you solve for number 3, and then you solve them for a number of times. Because if you're aware, these 3 things can be related to each other, right? Like I assume they have to happen at once. But if C go jogging before A go to sleep, then C will be too loud and A cannot sleep, okay? And A sleep, A will make the sound that will distract B, and B cannot study, like that. So you would like to solve every constraint at once, but you cannot. So you use the iterative solver, which means that you solve them one by one and then repeatedly. This actually repeatedly. You put A to sleep, you tell B to study, you tell C to go jogging, and then A will be awake. Then you will have to put A to sleep again, and you will tell B to study again. Like you will have to continue the loop until that you are satisfied with the result. And as you continue, it's gonna converge, right? Like if you solve it for one time, the result you get might be very deviated from the actual solution. But if you solve it for a number of times, the more you solve, the more the solutions converge to what you want. That's the intuition. Converge as you solve it many times. Okay, that's the solvers. Then what do we have? We have the discretization, the numerical solution, the solvers. And then maybe I'll talk about rigid body. Okay, rigid body. Rigid body is something that you work a lot because you are mechatronics, right? You would like to simulate a robotic arm. I assume that I have a joint here. Oh, it is joint, not jot. It's joint. You have a joint here. You have a arm, and you connect it to another arm, right? And this arm you will connect it to a circle. I assume a circle. Okay, and I'll call this point. I'll call it A. This point is B, and this point is C. Okay, so rigid body, it will has constraints. It means that there will be certain things that you have to satisfy as one. The first constraint is that I assume C must stay static. Okay, let the length of the arm be C L0 and this one L1. Okay, and you have XB minus XC must equal L1 L0. Okay, it means that this means the length between B and C, it must be L0, and also the length between XA minus XB, it has to be L1. And this is a set of constraints that you have to solve when you are simulating this robot arm. And to represent the constraints, we use matrix. So matrix là ma trận ấy. Vậy thì why do we have to use matrix? I assume that we have a set, right? We have this one. We would like to solve for XA, XB, and XC. Okay. This is what we want to solve. And as you can see, each of XA will be consist of 3 elements, right? It's gonna be XA, YA, ZA, and XB gonna be XB, Y, the vector, and ZB, and etc. Okay. So how can you solve this simultaneously? You will have a constraint matrix. And inside this matrix, we will have constraint data. You can find some video about linear algebra that will on the YouTube. There are 3 blue, 1 brown. It is a very good YouTube channel in order you to learn about these matrices. So matrix is basically a function that you can multiply it to a vector, and you will output another vector. Okay, it's due to transform. You will have a set of things you want to solve. A matrix of constraint data. It means that however you move A, B, and C, you will have to satisfy this matrix. And the second one is the transformation matrix. And this is how you like to move your solid. Okay. A matrix is a mathematical identity that you can store data and vectors there, and you can let the matrix interact with vectors or with other matrices in order to get the result you want. So you will have to learn linear algebra in order to use these matrices, but I would say that this is the core of rigid body simulation. You must learn linear algebra. Hoặc là nó là đại số tuyến tính đấy. Đó. Okay. You have to learn how to use your matrices. Rồi. This rigid body. You solve for constraints. Rồi, ok. Chắc lý thuyết vậy thôi nhỉ. Vui thôi. Có câu hỏi gì không? Sao có anh em nào muốn... Ôi, chết mẹ. Nhấn nhầm anh em ơi, nhấn nhầm. Ok, có ai hỏi gì không ta? Ý là không phải hỏi mà có ai muốn bàn luận gì không? Ok không? Đó là một số những concepts mà anh em sẽ gặp. Sao nhỉ? Có ai muốn nói gì không? Ok nhá. Okay.
Tại chưa
What? Sao?
đâu không có đâu, hiện tại chưa có gì để hỏi. Tại
Okay.
đa phần mấy cái gọi là cái concept trong này phải tự tìm hiểu thêm được nữa mới được, chứ bây giờ nghe cũng hiểu sơ sơ.
Okay. Okay. And in order to simulate to do the your midterm test, you will use this one, this one, and you will use an explicit solver. Đâu rồi? Here, here, here. And I'll teach you more. Okay, I'll teach you more about how to use this in practice, and I'll show the project of my team. Okay. I'll code this from the beginning. Like this is the result. This is the result, and I'll summarize it. Còn nhóm ta, ok, solvers rồi rigid body. Ok, mình sẽ cho các bạn xem một cái ví dụ về một cái thứ mà chúng ta phải phân tích ra nha. Spatial discretization đấy. Đây là một cái mô phỏng chất lỏng. Ok chưa? Và khi mình nhìn đây nè, mình sẽ thấy á là nó là một cái mảng, gọi là một cái mảng chất lỏng, nó continuous. Nhưng mà khi mà mình tách ra, thực chất nó lại là những cái hạt rất là nhỏ, thấy không? Có thấy không vậy? Mọi người thấy không?
Ok.
Đó. Thì yeah, we have particles, and we will use the solvers. We use the constraint in order to force the particle to not be too close to each other and not be too far either. And we will have a particle system. And then when you apply some random trick, hold up, where is my particle? Okay, and then when you use your computer to render this, it's gonna be a continuous field like this. Okay, but basically it is always some discrete particles moving with a fixed time step and spatial discretization. Okay, that's my project. We'll save it for later. Rồi, MATLAB tắt đi nha, code lại cho uy tín nha. Rồi, okay, first I will give you the prompt of our team, the MATLAB prompt of our team. Project 3, project 8 here. Ok, so cái đề này nó nói cái gì? Nó kêu là the relationship between an electrical field and the electric potential is represented by E equal minus gradient of V. Oh, I forgot one thing. Talk about gradients. I forgot to talk about gradients. Okay. The last thing, we will have gradients. We will talk about some basic mathematical notion. First, I assume that you all know the derivative, right? That the derivative is basically you measure the change of x over a infinitesimal amount of t, and it's gonna be the slope. It's gonna be the slope, right? Then you will have integral. Integral is the opposite of derivative. You will have x will be equals to the integral of the derivative of x over dt, or basically is the integral of v dt, right? And if you have the v and the t, then the x will basically be the area of this function, right? And then what do you have? You have gradients. Some of you might be familiar with this, and some of you don't. But I'll give a brief talk about this. Gradient, the symbol is the upside down triangle, right? This, and it's gonna be a vector. It is a vector. Why is that? This vector equal d over dx I plus d over dy j plus d over dz and k. Okay. The gradient basically measure how fast a value changes in space. Okay, because the form of the gradient, meaning that it will take a scalar, like it will take a scalar, and it will return a vector. Like this term d over dx, meaning that I will move this scalar v in the x direction a very small point, and I will measure the rate of change in that direction, and I will multiply it by the I vector, which is the unit vector in the OX axis, right? And then I will have a vector that represents the direction and the rate of change of my scalar in that x direction. And then I have d over dy, the same meaning. You will have a vector pointing in the y direction, telling you how fast or how slow your value is changing in the y-axis. And then you have the d over dz is the same. It's basically the same. And how fast the value change, it will return a vector. Okay. It is basically a set of derivatives. Then you will have integral, not integral. You have divergence. Divergence is also a upside down triangle, but it is a scalar. It's not a vector, it is scalar. And when you take the divergence of a vector, meaning that you will return a scalar. Okay, so the divergence measure how much that vector diverges. Okay, I assume that you have this vector field. Okay, this vector field. You can easily see that every vector in this vector field is pointing away from this point, which means that the vectors here have the tendency to diverge away from the point that you are examining. So this point, the divergence is vector E will be positive. Okay, divergence measure how much the vector field diverges from a point. And in the opposite, if I have a point and every vector is pointing at it, then the divergence gonna be less than 0. Okay. So what this is saying? This is saying that the electric field is equal to the minus gradients of a potential field. This is a physics sense, but you can understand it as this. Like if you have a charge, if you have a space that is charged, then it's gonna have a electric potential in it, right? It's gonna have energy. And if there is a change in the energy in your space, then that change in energy will create a electric field, which means the electric field is a vector created by the difference in the electric potential. Okay. And because of this electric field, particles will have the tendency, the positive charge particle will have the tendency to move from the from places that have high electric potential to the lower ones, because the difference in the potential creates the E vector, and it's minus because if you use Maxwell, it's not Maxwell maybe, learn more physics to understand. Okay, but this gives us the equation, which means that if we have a v vector, right? If we have a not a v vector, a v scalar, and v will be a function of x and y, then your E could equal the minus of the gradient of v, and it's gonna be dv over dx I minus dv over dy j. Okay, and this is how you can compute your electric field. You will take the derivative of v with respect to x, you minus it by the I and this by the y. Okay, and this also gives us a formula to calculate the energy density using the E vector. Okay, and you will have to allow the user to input v, x and y. It can be any function, can be anything. Okay, and then I will have to plot a electric potential map, and then I will have to plot the electric density field on the map, which means that I will have to calculate the E vector, and then I will calculate the magnitude of it at any point in the space, and I will show it onto the graph. That's basically what this task is asking me to do. And what do? I will put this next to my code so that you can easily follow the criteria. First, you will have to write a function of v, right? It say enter any expression as a function. I must allow the user to input any. So I'll see that my x and y will be the variable. And in order to declare a variable in MATLAB, you will say sims xy. Sim xy. And MATLAB will understand that, okay, from now on, whenever you use x and y in your code, it's gonna be the variable that you can substitute a number into and you get a value. Then you would declare a function. You could say v equals x to the power of 2 plus y to the power of 2, for example. Okay, and remember, this can be an arbitrary function. Okay, then what you do, you have to create a mesh. What is a mesh? A mesh is basically a XYZ map that you can plot the value on the Z axis and the coordinate on the X and Y axis. I will give you some image of the map of the mesh. This is the mesh plot. Here's the mesh, which means that this is living in the third dimension, but actually it only take account of x and y axis, and on the z axis is plotting the value that you are examining at a point. Okay, so a point in the mesh could have this form. A point in a 3D mesh could be I assume it's a, okay, you're gonna take the coordinate xa, ya, and the a value, any value. Okay, so how to do the mesh? I said that if we want to draw something, we will have to discretize our space, right? So we will use x value. We will first have to declare a set of x, like instead of calculating the v value for every x positions, I will just calculate it in x equals 0.1, 0.2, 0.3, 0.4, right? I will have to discretize the x-axis first, and the comment for that is linspace. X-bound, and step. Okay, and what this do? It will create a uniform set of x values ranging from the minus x bound to positive x bound, and the number of x values will be defined by our step. I assume I can declare x bounds equal 100, and my step can be 100, which means that my x will range from minus 100 to 100, and there gonna be 100 values of x that I'm plotting. It can be like minus 100, minus 98, minus 96, minus 94, right? It means that it's not infinite, it's finite. Then I'll do the same for the y values. Linspace of minus y bound, and step. Okay, so my plot would look like this. I will have a xy here, x and y, x is y. My x gonna go from 100, then minus 98, minus 96, blah blah blah, to 0, and it's gonna be to 96, 98, and 100. Okay, and similarly my y will be 100, 98, 96, blah blah blah, and this is gonna be minus 96, minus 98, minus 100, right? And I will calculate the value of the points just in those set of coordinates. I won't evaluate every point in the space. Okay. Then what more? Then you can create a mesh grid. Of x values and y values. What this do? Basically, your x values is just values, right? Your y also, and this mesh grid function, it will create a matrix, store every possible point in your domain. I assume that here you will have a set of possible points. It's gonna be 100, right? And are gonna be 198, 196, blah blah blah, to 100 and minus 98, 100 minus 100, right? And blah 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 gonna be minus 800, 100, minus 898, blah blah blah, to minus 800, minus 800. Okay, so basically after you have a set of possible points of x and y, you would like to create a set of 2D coordinates, and you will use this position to get your potential field. That's that. And here x and y will be a set of points, a matrix, but if you're not acquainted to that, you can just imagine it is a set of possible points on the x direction and the y direction, every point in space. And if I reckon correctly, it's gonna be 100 to the power of 2. It's gonna be like 10,000 points. Then what you do? You would like to substitute every point in this set into your v function, right? So that you can have a set of v values of the potential electric value of all the points you created here, and you will say v values will equal to substitute v x y x y. Okay, here it means that you are substituting all the points in the x and y into your v function, which takes the variable of x and y lowercase, right? This is like substitute, and here now your v values will be a matrix containing 10,000 different electric potential values corresponding to 10,000 discrete space that you created earlier, and you will have to convert this into a double. Double is just a format, like when you declare a variable, this is gonna be a symbol, right? A symbol is that something you can substitute in, and a double is a number, is a float number. So basically you have to code double to convert this v into a set of actual numbers instead of just functions. Now you have the v values. How you gonna get the e, right? You can do this. You can find the because you know that the e is equal to the gradient of v, and we have to take the derivative. So first we would like to find the function for the derivative of v on the x-axis. I will call it the vx diff, and it's gonna be the function diff, the differentiation of v with respect to the x variable. Okay. And similarly, vy will be equal to vy diff v and y. Diff is a built-in function in MATLAB for you to evaluate the derivative of an arbitrary function that you input in. Okay. Then this is gonna be functions. This is gonna be the functions, and just like we did with the v values, we will use the ex will be equal to minus double. We substitute the function vx diff with our variables, with our points x and y. That's it. And similarly, you do the x y. Okay. ey minus double subs of what? Vy diff x y and xy. That's it. Now you have the set of values for v, for ex and ey for any point in the space you created. Now you would like to calculate the magnitude of the electric field by taking the E magnitude. It will equal to the square root of EX square plus EY square. Why do I have a dot here? Because EX and EY is not a scalar. It is a matrix, right? It is a matrix. So you have to use the dot to perform an element-wise matrix multiplication, which means that this power of 2, it won't be applied for just for any specific value in this matrix. It will be applied for all the elements inside here. Okay? If you don't have this dot, there will be an error. You cannot raise a matrix, but you can perform element-wise multiplication, which means that you apply this power of 2 to each value in your matrix. I assume that in EX we have 1, 2, 3, 4, okay? And after we do the element-wise multiplication, it's gonna be 1, 4, 9, and 16. Yeah, we raise every element in the matrix. I know it is kind of hard to follow. So like EX, okay, it's gonna be a matrix that have the value 1, 2, 3, 4. And if I take EX, I do the element-wise power of 2, which means that I am raising each element here to 2. And it's gonna be 1, 4, 9, and 16. If I don't have the dot here, it's gonna be the full set power of 2, and it's gonna be something else, something different, something else, right? We don't want this, we want this. That's why. Okay. Okay. We got the E magnitude, then we can compute the E row. E row is the U here. Is the U here. Okay. I'll call it, okay, E row. Rho is the density, and U here mean the energy density. So I'll call it E row. And I'll follow the paper. It says that E0 divided by 2 multiplied by the Emax. And again, I'll have to raise the Emax by 2 and I'll perform element-wise multiplication. It is the E row. And remember to declare every constant that you say here. E0, I'll have to declare it here. I'll use E0 equal A.A54 no. Okay. Y bound 100. That's it. Then we have everything we need. We have the points in the space, discrete points. We have the value attached to each point. So it's time to plot our figure. How to plot our figure? First, we declare a figure. Okay. Then we can set the position of the figure. This is optional. Okay, I will leave it. Then you know that we would like to plot two graphs, right? We would like to plot first the potential, the electric potential here, and then we would like to plot the electric energy field. It is two different graphs, so I will put two graphs onto one figure. And how do I do that? I'll call subplot. Subplot is basically you declare what you want to graph and where you want it to be drawn. Subplot 1, it means that draw this plot on figure number 1. Okay, and this figure gonna have two plots, two graph. Okay, I'll call the window. This window is number 1, and this window will contain two graphs, and this graph will be the first one. Đó. Đây là cái cửa sổ số 1. Cửa sổ này sẽ gồm hai cái graph, và cái graph mà tao sắp vẽ nè là cái graph số 1. Okay chưa? And the command to draw a function, a mesh is surf. I will input the x, which is the matrix storing all the points in the x direction, okay? The y and the v values according to those direction. And I can set the title. The title will be like potential distribution, right? Then I'll have the x label. X label is that I'm naming the name of the x-axis. I'll call it basically x, right? And y label, I'll call it y. And z label, I'll call it z. Okay. Then I'll have the color bar. Color bar is basically a bar telling you that what color corresponding to which amount, and you will understand it as soon as I click play. Okay, I will press play here and you will see what it go. I have to okay, I have to add the path. But okay, I got a beautiful graph here, right? Here's my graph. And what this say? It means that here from minus 100 to 100, this is the x-axis, this is the y-axis, and this is the z-axis. Okay. Okay. Wait. Hold up. Let me rename them label, and let the z be the v of x and y. Run. Okay. As you can see, this is not continuous, right? It is divided into grids because on the x-axis I have the value from minus 100 to 100, but actually I only have 100 points inside here, which means I don't have negative 99. I don't have 1, I don't have 3, I don't have 5. I only have even numbers. I only have 2, 4, 6, 8, 10, and the same goes for the y-axis. So that's why I call this discretization. You have to divide your space into grids, and the z-axis here show the magnitude of your potential field, okay? Which means that the low point here at x and y equals 0, the v is 0, and then when I move further from my origin, the v value increases. This color bar tells you which color corresponding to what value. The blue here is the lowest one, and as it gets more yellow, it gets higher here. And you can increase the domain. You can do two things to increase the quality of your plot. Giãn lại khúc figure cho xuống. Okay. Here's the figure. First, you declare the figure. Then you declare the subplot. The first, you will input 3 things here. The first number will tell you which window you are currently at. So I'm at window number 1, cửa sổ số 1. Then the second parameter is how many graphs you would like to put into that window. I would like to put two graphs into one window. So you can see the graph, 2 graphs into my window. And the third parameter is that what is the position of this currently graph. I would want to put it in the first position, okay? The number of window, the number of graph, and the number of my current graph. And I will use surf function to draw my mesh. It's gonna take the matrix of the x points, matrix of y points. You can search online, you can search for mesh matrices. You can see a more intuitive explain about these x and y. and this is the v values corresponding to all the points. And this section is me coloring my graph. I call the title, I name the x, the y, the z, and I set the color bar. That's it. Okay. Okay. And this is my graph. And how can I increase the precision of this graph? I can put more steps, right? If I do more steps, it means that I take account of more points in the space. And if I increase the number of steps by 10, you can easily see that it's gonna take longer to respond, because more steps mean that your computer will have to work more, and maybe this is too much, right? This is too much. Okay, maybe 200 is okay. I'll try 200. 200. Hold up. Let me speak with my girlfriend. Hold up. Let me speak with my girlfriend. Do you have a girlfriend? Okay. Here, you can see that our graph is much more detailed, right? Only with 200 steps, and it looks much more detailed. Here, the grids are now smaller, and it represents a more continuous field of electric potential. That's why I say that you have to consider both the cost to compute and the accuracy you want. You have to balance them, because as you saw, if I input 1,000 steps, my computer gonna explode, right? So maybe 200 is okay. It looks good. Okay, I'll go back to 100 because it's faster. And that's my potential distribution. How do I plot my electric field? Just the same. I will call subplot, and I would like to answer window 1. My window got 2 graphs, and this is going to be graph number 2. I will solve. I will have the same x and y set point, and I will input the E row. E row is now the density value, the energy density value. And I'll title it. Title. I'll say this is energy distribution. Okay. And X label, I can say X. Y label, I can say Y. And Z label, I can say energy density and color bar. And you can say that we have 2 plots. We will have 2 graphs on the right hand side and the left hand side. And that's the end of the assignment. It's really easy, right? Here. Okay. The left one shows the magnitude of the potential value over my x and y domain, and the right hand side show the energy distribution value. And you can see that the value of the energy here is very low. Okay, maybe it's low because we are examining a small portion of space, or maybe our potential field is not big enough. Okay, so this is the energy distribution. The further away from the origin, the more energy the space have due to the electric phenomenon. Okay, and that's the end of our task, but I don't like to stop there because it's too easy. As you can see, I only used 40 code lines and I finished my midterm test. It's too easy for me, so I don't like it. But I'll tell you about something more. Okay, you can position your window with this code. You can say set GCF tag position, and you can position it. I position it at 20, 100. These are the x and y coordinates of the upper left corner, right? And then the width and the height. Okay, that's how you set. That's how you initialize your window. Bigger, better. Then one more thing, I would really like to plot the to use the explicit. Okay, I would really like to show you how I use this explicit solver, because I have seen most of your tests, most of the problem, or to be exact, problem 1 and problem 12, it includes this explicit solver. Like you will have to solve a differential equation, and you have to solve for the position, the data of a point mass in space. But my project doesn't have it, so maybe I'll have to have another talk in the next week, maybe, if you want to hear. Now I will end my project with one more thing. Is that okay? Now I had the energy and the potential distribution, but that's not enough to examine a electric field in space. I would like to see how are the vectors, the E vectors, right? Because the E vectors, the electric field vectors, is the thing that determine the force acting on the charged particle in space, right? So I would like to see that, and I will add something. I will add the E vector here, so I can do like this. I can use hold on. It's like wait, don't end the program here. Don't what? Okay. This hold on here is like don't close the window here. I will add something onto that window, and I can use the quiver. Quiver is like drawing arrows. And if you ask why I know everything here, because I use ChatGPT. Actually, the last time that I used MATLAB was like 6 months ago. But I know the concept and I know how to use AI. So I've learned everything here in 20 minutes. But that's a skill to learn, and I'll talk more about actually how you can learn to code effectively in the next talk if you'd like to hear me. Okay, back to this. Quiver is the arrow vector. Then I'll input the x, y, the y. This will be the origin of the vector that I'm pointing to, and I will input in the ex and the ey, right? Because it's ex and ey is basically the magnitude in the x and y direction. So quiver will draw an arrow. We will have to input the origin, the xy coordinates of the arrow, and we will input where the tip of the arrow will land, ex and ey. Okay, and we will draw the arrow in the red color, and we will say hold off. That's it. And you will see now we will have the arrows here, super tiny arrows, right? These arrows will point in the direction of the electric field in that position in space. But what if it's too small that I cannot track it? I will have to discretize the space in less blocks so that my arrow can be bigger. And how do I do it? Like instead of using the initial x and y quantities, I can use the x sub is a smaller set of x, and I will still use the x but I will only use the value from 1 to the spacing to n, and also 1 to spacing to n. And my spacing will be spacing equal 5. What does it mean? It's like I am taking all the points that is stored in the X matrix that I created above, but instead of using every point, I will just use each point with the gap of 5. Okay, which means from the first value to the last value on the x x-axis, I will skip 5 values and I will use 1, skip 5, use 1. So it won't. So the step will be smaller and the step size will be larger. Okay. And why do I have to use 2 parameters here? Because the x is basically the matrices, and it's stored 2D values. So I will have to define the domain that I would like to use in the x values and the y values too. And then I can use y sub. Y sub, it is the y value, okay, and just the same spacing to the end, and 1 to spacing to the end. And I can use ex sub 2 because my ex matrix is corresponding to all the value in x. So if I downscale the x, I will have to downscale the ex too. So our ex sub is going to be ex 1 spacing and 1 spacing and also ey got to be ex 1 spacing and 1 spacing n. Okay, now instead of quivering the x y is y, we will quiver the x sub, y sub, ex sub, and ey sub. Now you can see a much more easier to look arrows here, right? Which means that you put less arrow, but you let each arrow to have more space. So if you look here, you can easily imagine how a particle would move in this field, right? You have the electric vectors, and you have the formula that F equals the charge multiplied by the electric vector, right? So if you put a particle here, you can see it move around. And actually, I have coded a code to plot the trajectory of the particle, but it's late, so I will end here. Okay, but I think that these vectors are necessary for you to understand this field. Okay, and how do I end this? Hold up. Potential distribution, energy distribution. Okay, that's it. Okay. I will try to change the function here and see how it takes. Maybe x plus y, a very simple function, and we will see that it has this shape, a flat plane, right? Because x plus y is basically the formula for a plane, so it's gonna have a plane here, and because the gradient of v is a constant, right? Because you know the derivative of a straight line is a constant, so the derivative of surface is also a constant too with respect to each axis, and your electric field will look like this, all pointing in the same direction with the same energy density. And if you take some crazy thing like the sine of y and you take the cosine of x, you can see a different output. Okay, here, what the fuck? Cosine and sine makes our function periodic, which means that it will take the periodic form over the space, and it will create this weird thing, right? But it's mesmerizing, right? And I guess each of these things is a sine wave. It is a sine wave. Okay, you can mess with this, You can go right like this, and you can the e of y is gonna be more fun to play around. That's it. And it satisfies the demand of the prompt here, that you will be able to plot any field by enter any express of the potential. And remember, I was able to do this because I was take every v differentiation. Here I use the diff function so that I can input anything here, and the v diff and the vx diff and vy diff will be altered corresponding to my input. So that means that you have to generalize your code. Instead of like if I put x here and plus y here, and instead of using this function I use vdiff, I will to multiply by x plus y here, right? And this I will have x power of 2 plus 2 multiplied by y. This is not general, which means that if I change the initial function, this simulation will break down. So when you code, you have to keep your mind on the generalization of your code, so that if you change the variable here, the whole code will change according to that. Okay, and I think that's enough for the first talk here. I just want to share something with you, and there's thousands of things more to say if you like to follow, and maybe I'll teach you if you like. Okay, I'll start recording.